What exactly is virtual memory? Virtual memory is a critical concept in computer science that allows an operating system to create the illusion of having more memory than is physically available. We'll talk about the technical details a bit later, but first let's discuss paging, the fundamental memory management mechanism through which virtual memory is implemented in Windows. Paging involves dividing both virtual memory and physical memory into 4-kilobyte chunks. These chunks are known as pages in the case of virtual memory, or page frames in the case of physical memory. The 4-kilobyte chunk size is chosen based upon mathematical and optimization factors that are beyond the scope of this video. Windows supports two types of paging: disk paging with clustering and demand paging. Let's begin by discussing disk paging. When the system requires more physical memory than what is currently available, the memory manager moves around unused memory pages to special files, called page files, on disk to free up memory. This process is known as paging out memory or swapping. Paging out a memory region does not delete it from memory, its addresses remain valid. When an application attempts to access these addresses, the operating system retrieves the page from the page file on disk and moves it back into physical memory. However, since clustering is used, the memory manager moves not only the requested page, but also the surrounding pages into RAM. Put simply, disk paging uses the disk as a temporary extension of RAM. Now let's talk about demand paging. When a thread requests memory allocation, the memory manager does not immediately allocate memory, but instead returns a pointer to memory that has not yet been allocated. The memory is allocated only when it's accessed. This method is used because programs may request memory that they never access or use, and keeping such pages in memory wastes system resources. Next, let's delve into the concept of virtual address space. As discussed in the previous video on processes, Windows and many operating systems do not allow direct access to physical memory. Instead, they provide indirect access through a private virtual address space that each process has. So how does this virtual address space function? From this point on, everything we'll talk about pertains to 64-bit processors. Every process on Windows has its address space divided into two parts, the user mode address space and the kernel mode address space. Both of these address spaces can each address up to 128 terabytes. The black gap you see in between is unmapped memory addresses which cannot be mapped due to physical limitations. As discussed in the previous video, the user mode address space is reserved for mapping non-critical information related to a process, including the process environment block, the thread environment block, function arguments, and code. The kernel mode address space is allocated to store more crucial information like the handle table, the K and E process data structures, and more. In a typical setup, the user mode code cannot directly access or alter the kernel mode memory pages, which serves as a robust protective measure. However, it's important to note that any component running in kernel mode can read or modify data located anywhere in the user mode address space. The virtual address space of each process is private, meaning that process A cannot access the virtual address space of process B and vice versa. However, this is not the case in kernel mode. All operating system components and drivers running in kernel mode share the same virtual address space. This is why a lot of static data, or data which should not change, is marked as read-only, to prevent accidental overwriting. Windows has a protection mechanism called Data Execution Prevention, or DEP, which prevents malicious software from executing memory pages as code. If your processor supports DEP and it's enabled, then Windows will not allow any user mode code to execute memory pages as code, as is often done by malicious software to execute shellcode. To help you understand this better, let's look at an example. We have DEP enabled on our system. Some process allocates a memory page and writes some shellcode to it. Now, normally it will be able to execute this shellcode without any problems. However, since DEP is enabled, if the thread tries to execute this memory, it will throw an exception. Now, with the theory out of the way, let's see how to actually allocate and make use of virtual memory using the Windows API. This is the signature of the function that is used to allocate virtual memory. Let's dissect each of its arguments one by one. These in and out brackets specify whether the argument is going to receive data or return data. The return type of this function is LP void. LP stands for long pointer, so this function is going to return a void pointer to the allocated page. The first argument is LP address, which allows you to specify the starting location of your virtual memory page. If that memory location is not already used by anything else, then the memory manager will allocate your page at that location. This is an optional argument, meaning that you can pass null and the memory manager will choose where to put your page. The second argument is DW size, which allows you to specify the size of the allocation. This argument is going to be rounded up to the nearest page boundary, which is the nearest multiple of 4096. We'll discuss this more later in the video. The third argument is fallocation type, which allows you to set the type of the memory allocation. You will almost always set this to memory commit because all other options for this argument aren't very useful. Finally, the flProtect argument lets you specify the protection type that you want to have for your allocated page. This just refers to the access you want your page to have, like read-only or read-write. Another function that's going to be useful to you is virtual free. This function allows you to free allocated pages just as you free memory allocated by malloc. The arguments to this function are pretty similar. The first argument allows you to specify the location of the page you want to free. The second argument allows you to specify the size of the page. The third allows you to specify the type of allocation. And the last allows you to specify the protection of the allocation. So here's some example code that uses virtual alloc to allocate memory. As you can see, the first argument is set to null, which means that the memory manager will decide where to allocate the page. The size is set to 8, and the nearest multiple of 4096 is 4096. So the size of the allocated memory region will be 4 kilobytes. The allocation type is memcommit, and the protection is set to read-write, so you will be able to both read and write data from this page. If you execute this code, it will print the base address of the allocated virtual memory region. And that's all for this video. Thanks for watching, and make sure to check out guidedhacking.com for more tutorials like this one. See you next time.